We have already seen the principle of work and energy, and we said that sometimes also we can apply the conservation of mechanical energy if all forces doing work are conserved. Okay, so now let us do some practice on cases where we can apply conservation of mechanical energy. If you remember when we did the problem, this one, okay, just I will repeat an important idea in it. We had an airplane that was initially at an angle of 60 degrees with the vertical, and we released the airplane, and it has a clash with the ground when theta equal to 15 degrees. And we found together the tension of the cable at the last point when theta equal to 15. But the question was find the maximum tension. So we should justify why the maximum tension developed is at point B, which corresponds to theta equal 15 degrees. So if I go back to my problem, this is the figure. I have in my case, I have an airplane, and initially it has an angle with the vertical of 60 degrees. Okay, and when I cut cable AC, it will be released and it will go down until reaching the before reaching zero level. And it will clash when theta equal 15. It will clash with the ground, so we will have a shock, and then we want to find the velocity of B just before the shock. Okay. Now, at any position of my system, I can say that the only two forces acting on it. So I do the analysis for any value of theta. So if, for example, my airplane is in this position, this is the angle theta. Then, if I draw the free body diagram of forces acting on it, I have only two forces acting on my airplane. So wherever is the location I am considering, let us draw it together here. So if I want to draw the free body diagram, I have the weight, which is downward. So I have the weight that is downward. And I have the tension in the cable. And since my cable is doing with the vertical an angle of theta, okay, and the tension is along the cable, then I can say that the angle between the tension and the vertical, which is here equal to theta, is equal to this one here, okay? So the angle here between the vertical, so this is the vertical direction. This angle here is known to be theta, okay? So now, if I consider, I will put my UT-UN diagram, okay? If I want to put my UT-UN diagram, I have always UT is along my frame will be in a way that UT is always tangent to the path. So I have here a circular motion. Why I have a circular motion in this case? Because the radius is constant, the distance from this point here. So here, let us call this point, for example, this is point C. Okay, point C is fixed, and the distance between CA is always equal to 20 meters, which is the length of the chord. So the airplane is doing a rotation about C, which is fixed. Okay, and then I have a circular motion. So I can write UT-UN where the radius of curvature is always equal to 20 because it's a circular motion. Okay, and my vectors UT-UN are in this way. UT is always tangent to the path. Okay, so and UN is directed towards the center of rotation. So I will draw first, where is my center C? The center of my rotation is somewhere here above. It's along T. So T pass by the tension, pass by C. Okay. So I can say that UN will be the unit vector of the tension because both are directed towards center C. So this is vector tension and this is vector UN. On the other hand, UT is always tangent to the path. So UT is perpendicular to the radius, it's downward. Okay, so this is UT. And now all I have to do, I want to find where is the location of my maximum tension. This is why I should come up with a general relation for my tension. Okay, to come up with a general relation for my tension, I will write my equation. Since my tension is along UN, I will write sum of n, sum of forces along n equals to MAN. Okay, now what are the forces along UN? Of course, I have the tension, so plus T. And if you look at your figure, you have another force that is the weight. And the weight is doing an angle of theta with a UN. Okay, so if I project W on theta here, this is W. As you can see, the projection of W on theta will be in the negative UN direction. So if I do here my projection like this, I'm projecting the wave, I'm getting a negative component along UN. And since the angle here is known, this angle here is theta, then the projection is simply minus W cosine theta. Okay, so here, since I know that the angle here between W and UN is theta, and my projection of W on UN is in the negative direction, so I can write that I have T minus W cosine of the angle theta equals to mv square over rho over r. The radius of curvature here is equal to the radius of circle, which is 20. Okay, what can you conclude from this relation? You can find the expression of T. So T is equal to omega cosine theta plus mv square over r. And as you can see here, okay, first from the principle of work and from the conservation of energy, or from principle of work and energy, we can demonstrate that more we go down, velocity increase. Okay, why? Because when we go down, what will happen? The potential energy will be reduced, and then due to conservation of energy, the kinetic energy will be increased. Okay, so here when we go down, what will happen? When the airplane go down, when airplane go down, we have that theta decrease. Why? Because theta is the angle with the vertical. It was 60 and it will end up with 15. So theta, the angle theta decreases, and the velocity v increase. Okay, why? Because for the velocity, as we go down, the potential energy is reduced. Okay, since potential energy is converted into kinetic energy when we go down due to conservation of mechanical energy. Okay, it's converted to kinetic energy from due to conservation. Okay, due to conservation of mechanical energy. So what can you deduce now? If you look at your expression for T, as you go down, what will happen to theta? We said that as we go down, theta decreases. And when theta decreases, cosine theta increase. Okay? So when you go down, cosine theta increase and V increase, so T will increase. Okay? So we have demonstrated from the formula of T, which is W cosine theta plus mv square over r, that when we go down, theta, more we go down, theta will be higher, because the two components of T will increase, W cosine theta and mv square over r. So now we can say that the maximum tension takes place at the lower level, okay, which corresponds to point B, just before the clash. And then to find the tension at B, all we have to do is to replace, as we did in the previous session, we found velocity at B, okay, and we replaced into the equation of some Fn cosine theta by cosine 15 and Vb by its value we got from conservation of mechanical energy. So first you apply conservation of mechanical energy, you get the velocity. Then you replace the velocity in some Fn and angle theta by 15 to get T maximum. Okay, so the only step that you should add to this problem is that you should demonstrate that T maximum takes place at the lower limit. Okay, so now let us move to any question before I move to another problem. Okay, so now let us continue the problems. We have a smooth 2 kilogram polar sea fits loosely on the vertical shaft. If the spring is unstretched when the collar is in the position A, determine the speed at which the collar is moving when y is equal to 1 meter. If first A is released from rest at A, and second, if it's released at A with an upward velocity of 2 meters per second. Okay, so here, first they said our collar is smooth. So we have a smooth collar. Okay, since the collar is smooth, this means what? No friction. So I can deduce from this sentence that no friction is acting on my collar. Okay, now we have that at the initial position, my collar was at A. Okay, so this is state 1. What do I know about state 1? I can summarize here the different conditions. So at state 1, I have the following conditions. First, I have that the velocity, in the first question they said it is released from rest. So VA equals to 0. And they said that at this position, the spring is unstretched. Okay, so because the spring is unstretched at A, so delta L of the spring at A is 0. Okay, so these are the two conditions at state 1. Now at state 2, we want to find what will be the corresponding velocity. So at state 2, the velocity is unknown. Okay, state 2, VC is not given and it should be calculated. And the other thing that we should find is delta L. So we should calculate delta L. We should calculate the spring stretching at this location, because here why we can apply the conservation of mechanical energy, because if we do the free body diagram of the block, what are the forces acting on it at any position? So if I take any intermediate position, okay, I will have the spring force directed, of course, towards B, because B is a fixed point of the spring. So I have F spring. I have the weight. Okay. Concerning the friction, no friction, because they said it's smooth. And don't forget the normal. Here we should have a normal reaction from the if you want, the rod on the collar. Okay. And who will tell me how will be this normal? It will be from it will act from which side? This one here, or this one? You have two sides. Okay, since you have two sides, you might be in contact with one of them. So here your collar is pushing when under the action of the spring, it will push on this side. Okay, because try to figure out what is happening. So as your collar is, you are pushing your collar towards the right, then it will do an action. The collar will do an action on this rod towards the if you want, to the right. So by it should do on it an action to the left. Okay, by action reaction, because since the collar is trying to push on the rod towards the right, then by action reaction the bar will do a force on the collar towards the left. Okay, so in this case the normal reaction from the rod on the collar will be towards the left, and it will be from this side here, the internal one here. So the normal will push the color in the opposite direction like this. Okay, this is the normal reaction. And if you, to make sure of your assumption, look, the color is not moving along x direction. So if you do sum of x equals 0, n should be in this direction, because to be able to oppose the component of x of the spring force. Because as you can see, the spring force will be divided into two components, one along x, and this one will be opposing n, since you don't have motion along x, and you have the y component of the spring force, but it will not be equal to the weight because you have a certain acceleration. Okay, so from here we can know how is the normal reaction and from which side it is applied, because to be able to push on the block towards the left, this surface should act on the color, this one, not the other, because the other surface can act in the opposite direction. Okay, so I will just now keep n. So n is like this here, from the surface on the color. Okay, but what is the work of n? What is the work of the normal reaction here in this problem? Work of n is equal to 0 since n is perpendicular to motion. Okay, since n is perpendicular to motion. So I only still have the work of the spring force and the weight. Okay, and I can say since the weight and the spring force are conservative, then I can apply the principle to conservation of mechanical energy. Okay, CEM, the abbreviation is CEM, conservation of mechanical energy, or CME. Okay, so here I can say that, so I can write that kinetic energy at point A plus gravitational potential energy at point A is equal to kinetic energy at point C plus potential energy at point C. And here in this problem, I have two sources of potential energy. I have the gravitational potential energy and I have the elastic potential energy. Okay, so I will divide VA into two parts. VA, I will say I have VA gravitational, okay, and I have VA elastic. Okay, so you have two type of potential energy, one due to the weight, one due to the spring. And from the other side also, I will say that from the other side at C I have the same. So I have kinetic energy at C plus potential energy, gravitational energy at C, and plus potential energy at C also. Okay, so now what I have to do, I will apply this relation on my problem. And I have two questions. In the first question, A is released from rest, while in the second question, it is released with an upward velocity of 2 meters per second. So in the two questions, the only difference will be in what? Will be in TA. Okay, so in the first question, I will put VA 0. In the second question, I will put VA 2 meters per second. So now let us replace term by term the components of our equation. So first, so TA, as we said, TA is equal to half m VA squared. Okay, so in part A, it will be equal to 0. Okay, in part A, TA will be equal to 0, while for part B, TA will be equal to 0.5 times 2, which is the mass of the color, times the velocity, which is 2 square. Okay, so this is, so you have, it will give you 4. Okay, so it will give you 4. Now, in the second term to find is the V gravitational at A. Okay, so the gravitational potential energy at position A. Whenever you need to define potential energy, you need to take a reference, a datum line. Okay, so here the best option is to take the initial position as reference, because this will simplify the calculation. Then here at this level the potential energy is 0. So since I selected my datum at the initial position of A, I can say that VA gravitational will be equal to 0. Okay, so this is equal to 0. And as I told you before, the choice of your reference will not affect your result. Okay, because at the end what you care for is delta Y. So whatever is my reference, at the end delta Y will be the same. So I have here VA gravitational equals to 0. Concerning, do you see the screen? Just 1 second, let me see what's happening. Okay, do you see it again?
Yes, now we can.
Okay. So we were talking about the gravitational potential. Okay, so we have at the initial position of A, we have, since we choose it as a reference, we have that VA gravitational is equal to 0. Now we want to find VC gravitational. So as you can see, they said that the color moved a distance of 1 meter. So we know that C is below the datum with a distance of 1 meter. Since it's below the datum, then it has a negative gravitational potential. So we can say that the gravitational potential at C is equal to minus mgy, okay, which is equal here to minus, so the mass is 2, g is 10, and y is 1. Okay, so it's minus 20. Now we still have to find the elastic energy at A and T. Okay, you have that VA elastic. You know that the elastic potential is simply half K delta L square. Okay, but from the given, they said that at the initial position the spring is unstretched. So what will happen is that delta A is 0 at the initial state. Okay, so since unstretched, so since the spring is unstretched at A, since the spring is unstretched at A, then we can say that V elastic at A is 0. Now we still need to find the elastic potential at C to complete all the unknown terms, and we will only have then VC as unknown in the conservation of mechanical energy. So the last term that we need to compute is V elastic at C. Okay, VC elastic. So we know that by definition the elastic potential energy is half K times delta L at point C square. Okay, and what is delta LC? Delta L at C is equal to total length of the spring, so L total of spring, minus L0, which is the unstretched length. Okay, so here What is the total length of the spring at position C? If you look at your figure, this BC, the distance from B to C, correspond to the total length of the spring at this state. Okay, so all I have to do is to calculate BC. And what is L0? They said that when the box was at A, it was unstretched. This means that AB is equal to L0. Okay, so I can say that delta L at C is equal to length of BC minus length of AB. Okay, and now if I replace, let us calculate BC. Okay, so for BC, what do we have? We have equals to radical. I do the Pythagorean theorem in triangle ABC. Radical of 0.75 square plus 1 square plus 1 square. Okay, and for L0 for AB it's given AB is equal to 0.75. So now all I have to do is to replace in delta LC and calculate the corresponding tension at point C. Okay, now once I calculate this, I can go back to my conservation of mechanical energy. Okay, so from conservation of mechanical energy, we said that what was the equation? We have TA at T at A plus V gravitational at A plus V elastic at A, and we found all of these, okay, equals T at C, the kinetic energy at C is 0.5 times the mass of the color, which is 2 here, times what? Times VC square, the velocity at C square. Okay, so here this is the only unknown remaining, plus V gravitational at C and plus V elastic at C. So now we have calculated VGA, VEA, and VGC, VEC, and TA was already calculated. So now our only unknown is VC. We get VC from the conservation of mechanical energy. Okay. Now, what will be the difference, as we said in the second step? The only difference, if we release A with an upward velocity of 2 meters per second, all terms will remain the same. Why? Because you have same initial and final position, but only TA will change. Okay, so the gravitational potential energies will remain the same since you have same positions, and also the elastic potential energies will remain the same. Only the kinetic energy of A will vary. Okay, so all you have to do to calculate the new value of VC for part B is to replace TA. Instead of saying TA is 0 because it's released from rest, you replace TA by half VA square. So VA is not 0, it's 2. So of course VC will change. And do you think that VC will increase or decrease if we release with 2 meters per second instead of velocity of 0? What will happen to VC in this case? What will happen? What will change in the velocity of C if instead of releasing at A from rest, we give an initial velocity? What will change? Look at your equation. Yes, exactly. VC will increase. Okay. Why VC will increase? Because as you can see here, VC is proportional to the square of VC is proportional to TA. So higher is the kinetic energy of A, higher will be the velocity of C. Okay. Now they said it is released with an upward velocity. What if we released it with a downward velocity? What will change? So if we release up A with 2 meters per second, or we release down A with 2 meters per second, what will change? Who can tell me? What will be the difference? will TA change? What is the kinetic energy of A? Kinetic energy of A is 0.5 mv at A squared. So since it's a square, if VA is plus 2 or VA is minus 2, TA will not change, and therefore also VC will not change. But why physically? How can I explain physically that if I give an initial velocity up, or I gave the same magnitude but I changed the sense of velocity, I will still obtain the same velocity at C. Why is this physically possible? Any idea? If you have friction on your system, it will be the same if you give an upward velocity or a downward one, do you think?
No, it wouldn't be the same.
Very good. Why it wouldn't be the same? Because when we have
Because your
friction,
acceleration isn't.
yes, because friction is a non-conservative force. So the work of friction will depend on the path of motion. So if you have a friction and you give an upward velocity, then your losses will be higher because you will lose energy when you go up, and also you will lose energy when you go down because friction is always opposing your motion. On the other hand, if you go directly from A to C, your path will be shorter and then you will lose less energy because we said that non-conservative forces are path dependent. Non non-conservative forces are path dependent. Okay, so they depend on the trajectory. Now, what we will do here, we don't have friction, so because all forces acting on our system are conservative, in this problem we have only conservative forces, and this means what? So whatever is the path of motion, the work will not change. Okay, in this problem we have only conservative forces doing work. Okay, conservative forces doing work. So their work is independent. So their work is independent of the path of motion. Okay, and this is why we can explain that the final velocity of C will not change if VA is plus 2 or minus 2, since we have the same energy for both. Okay, and the path is not important in our case because all forces are conservative. Okay, so this is the justification we can give here if they ask us why physically the two cases, if we blow A up or down, then we will end up with the same velocity at C. Okay, because the work of both weight and spring force are independent of the trajectory of motion. Okay, and if you apply and this is clear from your rule, when you write TA plus VA equals to TC plus VC, the only thing that will change if you pull A up or down is that VA here is plus 2. So in the first scenario, VA is plus 2, while in the second scenario, VA is minus 2. But if you replace in the equation, it will not make any difference because VA is square. Okay, this is why here the velocity at C at the end will not change. Okay, but as I told you, if I have friction in my problem, it becomes more complex. Okay, because if I have friction, the friction will depend on the path, and more I move, more I lose energy. Then of course, if I give a velocity up, I will reach a lower velocity at C because my path will be longer and my losses will be high. Okay, any question on this? So we are done with the dynamics part. Okay. So if you want, we have finished the program for this year. I posted for you. We did a lot of problems here in the slides. So understanding this problem is good. And for the review problems, since we might not have time to do all of them, okay? And to help you, what I will do, I have already recorded several problems in other from other classes, okay? Because I give the dynamics course also, and I have solved in detail for the dynamic class the problems of chapter 12, 13, and 14. So what I will do in order to help you in studying, I will post on our playlist, I will post my recording for solution of the review problem. So what I want you to do is now to start to study and try to solve. The review problems are a little bit complex, so don't worry if you don't directly know to do them, it's fine. So what I advise you to do is first to do again the slides we did together, okay? And then to just watch the videos of my explanation for review problems, because if you understand them, then you will be able to solve any other problem. And the level of the exam will not be as hard as the review, but the review, if you want, will help you to find other problems easy. Okay, so now I will post these sessions we did together. Plus, I will post the solution for review problems, recording of solution for these problems. And whenever you have any question, and if you are facing any difficulty, you can directly, or we do a session, our office hours, the Zoom session, or you can directly contact me by WhatsApp. You just take a screenshot of the problem and tell me what was your issue, and I will directly answer. Okay, so we are done. So no need to have a class on Monday, but anytime you need any help, I am available. So on WhatsApp, or I can open Zoom with you if you feel need. Okay, and good luck for the exam. I will name Ari, you mean all the previous one, or it's fine for the previous one? You want me to rename the previous videos or only the new ones that I will post? Okay, I will name the new ones. Yes, of course. Okay. Okay, so if you need anything, just contact me and I will help you. Okay? Yeah, good luck for studying. Bye.
Thank you, doctor. Have a
Welcome.
good day.
Bye.
Thank you, doctor.
Welcome.